Hello and welcome to part 2 of our Easter double bill. In part 1, we looked at Bede's account of the Synod of Whitby, where there was a heated debate about the correct method for calculating the date of Easter. The link to part 1 is in the description, so you may want to go and watch that before moving on into this video. Here in part 2, we'll look in detail at how the date of Easter would have been calculated by the winning side at Whitby. The name for the set of calculations used for important dates in the Christian calendar, including Easter, is the Computus, and a particularly important figure was a 6th century monk from the Eastern Roman Empire, Dionysius Exiguus, whom you can see there in the top left corner. His Argumenta Paschalia give a detailed set of instructions for a number of calculations relating to Easter, and we're mainly going to be looking at this source. Bede himself wrote a work, De Temporum Ratione, on the reckoning of time, which builds on Dionysius' work, but it's a lot less concise, so we'll only use that occasionally. Dionysius almost certainly wrote his work in the year 525 AD because he normally uses this year as an example for his calculations, as we'll see in a minute. Before we get into the calculations, there are a couple of key things to know. First, the Computus relies on the Metonic cycle. This is a cycle of 19 solar years, which is used to reconcile the solar and lunar calendars. Solar years are longer than lunar years, but if you add a month to the lunar calendar every time this difference in length is added up to a month, then you get a period of almost exactly 19 solar years, give or take a few hours, after which the difference will have reset. We'll see this at work in a minute, but the upshot is that any year can be numbered from 1 to 19, and we'll have to do this as part of calculating Easter. The cycle is named after an Athenian of the 5th century BC, Metone, but he didn't actually discover it, he just made some adjustments to apply it to the Athenian calendar. Another term which will be important is the 14th Paschal moon. This is the 14th moon about which we are hearing so much at the Synod of Whitby in part 1. The 14th moon of the first month of the Jewish calendar. It's called Paschal because the Greek translation of the word for Passover is Pascha. Since Easter was initially tied to Passover, this name just became the word for Easter in Greek and Latin. You might have noticed it crop up a few times in Bede's Latin version of the Synod of Whitby in part 1. And if you look at the open book behind Dionysius, you'll see that the adjective Paschalis is actually the first word. A final thing to remember is that we're going to be doing a fair amount of division as part of our calculations. The important thing is almost never the whole number which results from the division, but the remainder. And if you use a calculator to do divisions, you can still find the remainder quite easily, even if it gives you a decimal. Just times the number after the decimal point by the number you divided by initially, and this gives the remainder. So if you divide 15 by 7, you get 2.142, etc. Now if you times the number after the point by 7, you get 1, and of course 15 divided by 7 is 2, remainder 1. Oh, and a final thing is that we're dealing with the Julian calendar here. Catholic Western Europe adopted the Gregorian calendar in the late 16th century, and most of Protestant Europe followed in the 18th century. So, unless you're a member of an Orthodox church, I'm afraid this method won't get you a correct Easter date in the 21st century. And even if you are a member of an Orthodox church, you'll have to do a bit of extra work, but we'll talk about that later. If you've got all that, strap in, because it's about to get mathsy. Just to make things extra fun, we're going to jump right in at the final calculations for Easter, which might make you question why you ever started watching this video. But in a few minutes' time, I promise you'll know what all the jargon means, and you'll think the calculations are easy. So in section 14 of the Argumenta Paschalia, Dionysius runs through how to calculate Easter in the first 3 years of the cycle. We'll ignore 1 for now because it has an added complication, but here's year 2. In this year, the 14th Paschal moon falls in the month of March. Always take a required 36 in this month, and always subtract the epacts, 11. This leaves 25. The 14th Paschal moon occurs on the 25th day from the calends of March, that is, the 8th day before the calends of April. Take the above-mentioned 25 and add the 5 concurrents for the same year, which makes 30. Finally, always add a required 4 for this month, and divide the result by 7, which in this case is 7 4s, 28, with a remainder of 6. The 14th Paschal moon occurs on the 6th day of the week, and Easter Sunday is on the 16th moon. Well, okay, that's all a bit overwhelming. What are epacts? What are concurrents? We'll get there soon. But if you're not familiar with Roman dates, the calends is just the first of the month, and Romans counted inclusively. So to them, the 25th of March was the 8th day before the 1st of April. Before we make sense of all this, let's look at year 3. Again, the 14th Paschal moon is in April in the third year of the 19-year cycle. Always take a required 35 first of all in this month. Subtract the 22 epacts for this same year, which leaves 13. The 14th Paschal moon occurs on the 13th day of the month, that is, on the Ides of April. Take this 13 and add the 6 concurrents, which makes 19. In April, always then add a required 7, which makes 26. Divide this by 7, which in this case is 3 7s, 21, with a remainder of 5. The 14th Paschal moon will be on the 5th day of the week, and Easter Sunday is on the 17th moon. Well, it hasn't got any easier yet. So far we can see that we're doing slightly different calculations, depending on whether the 14th Paschal moon falls in March or April. And to make matters more complicated, what he doesn't tell us explicitly here is that these are example second and third years. So some things will always be the same in any second year, or any third year, but others won't. Now I really do promise that we've come to the worst point. From now on, everything we'll see will make the picture a little bit clearer. Let's start by extracting the useful information from these last two bits of text. If the 14th Paschal moon falls in March, we have to subtract the number of epacts from 36, which gives the date of the 14th Paschal moon. Don't worry, I know we don't know what epacts are yet, but we're getting there. Next, we add the number of concurrents to this date, and then add 4. Again, we don't know what concurrents are yet, but we will do. Finally, we divide the result of this addition by 7, and the remainder gives us the day of the week on which the 14th Paschal moon falls. If the 14th Paschal moon falls in April, we have to subtract the epacts from 35, and the result is the date of the 14th Paschal moon. Next, we add the concurrents to the date, and then add 7. Finally, we divide the result of this addition by 7, and the remainder gives us the day of the week on which the 14th Paschal moon falls. And a couple of things need bearing in mind regardless of whether we're in March or April. First, when we make our final division, we have to treat Sunday as the first day of the week, so Monday is 2, Tuesday is 3, and so on. This means that if there's no remainder, it's the 7th day, which for our purposes is Saturday. The most important point, and Wilfrith went on about this at the Synod of Whitby in part 1, is that Easter Sunday is the first Sunday after the 14th moon. So, if one year the calculations gave you the 14th moon on a Saturday the 29th of March, then Easter Sunday would be on the 30th of March. But if the 14th moon fell on that Sunday, the 30th of March, then Easter Sunday would be on the 6th of April, a whole week later. Okay, so we're a bit closer to knowing what to do now, but there are still a few things to work out. How do we know whether the 14th Paschal moon falls in March or April? What are epacts, and how do we work out how many of them there are? And what are concurrents, and how do we work out how many of these there are? Well, let's start with the question about March and April. Dionysius tells us, if you wish to know in which years of the 19-year cycle the 14th Paschal moon occurs in the month of March, in year 2, 5, 7, 10, 13, 16, and 18, you will find it in the month of March. In the remaining 12, you will unerringly calculate it in the month of April. Okay, that's clear enough. But the obvious question is, how do we work out what year in the cycle we have? Well, if you wish to know what number year it is in the cycle of 19 years, take the years of the Lord, say 525, and always add 1, which makes 526. Divide this by 19, which leaves a remainder of 13. It is the 13th year of the 19-year cycle. If nothing remains, it's the 19th. So, to sum up, add 1 to the number of the year, divide the result by 19, and the remainder is the year of the cycle. Just as we saw before, no remainder in one of these divisions means that we have the highest possible number. In this case, no remainder would mean the 19th year of the cycle. Well, that's sorted then, so let's move on to epacts. Dionysius is a bit vague about what epacts actually are, Presumably he expects us to know what they are already. So let's look at what Bede has to say. Lunar epacts are accustomed to add on to the course of the sun by 11 days annually. Because of this, they are called by the Greek word epacti, that is, additions, because, as we said, they are accumulated by the addition of 11 days each year. So, to sum up, epacts, or lunar epacts, are the number of days by which the length of the solar year exceeds the length of the lunar year, or, to put it the other way round, the number of days that have passed at the start of the lunar year by the time the solar year begins. These are cumulative, and they're increased by 11 each year, and they are what run in the 19-year cycle. In other words, year 1 will always have no epacts, year 2 will always have 11, and so on. Well, how do we calculate the number of epacts then? We can probably remember years 1, 2, and 3 of a cycle, 0, 11, 22, but beyond that it gets a bit harder, so here's what Dionysius tells us to do. If you wish to work out how many epacts there are, that is, lunar additions, take the years from the incarnation of our Lord, Jesus Christ, of which there have been 525. Divide these by 19, which leaves a remainder of 12. Multiply this by 11, which makes 132. Divide this again by 30, which leaves a remainder of 12. There are 12 lunar additions. So let's extract the general rule from this then. First, divide the number of the year by 19. Then, multiply the remainder by 11. Next, divide the result by 30. And, as always, it's the remainder that matters. And this, the remainder, gives us the number of epacts. You might have spotted a potential problem. What happens if the number of the year is divisible by 19? Will a remainder of 0 from the first step break the calculation? Well, happily no. In this case, there are just no epacts. You can times 11 by 0 to give 0, and then divide 0 by 30 to get 0, or, I suppose, a remainder of 30. And either 30 or 0 at this stage is fine, because once the epacts have added up to 30, the lunar calendar adds a 30-day intercalary month to address the disparity, and this reduces the number by 30. So if the years have gone 0 epacts, 11 epacts, 22 epacts, then the next increase of 11 takes us over the 30 mark to 33. But we reduce the number by 30, so every fourth year in the cycle has 3 epacts. This rule works all the way through the cycle, except between the 19th year and the first year. Because the 19-year cycle is a few hours away from being perfectly matched up to a whole number of lunar months, we have to add an extra epact. So the 19th year has 18 epacts, and then the first year has 30, or none, rather than 29. But that's only a problem if you try to work out the number of epacts by starting from year 1 and adding on 11 each time until you get to the year you want. As we've seen, a year which is divisible by 19, i.e. year 1 in the cycle, gives a result of no epacts if you use Dionysius' method, not 29 epacts. And no epacts is the right answer and what we want. Well, that's epacts sorted, so now we just need to look at concurrents. First, what are they? We're returning to Bede again here because he gives more detail on this. Epacts of the sun, that is, concurrent days of the week, always increase by the addition of 1 for 3 years, but by 2 each leap year, up to the number of 7. Their cycle contains 4 times 7 years, that is, 28, because, of course, it cannot be completed before the leap day, which is accustomed to return in the 4th year, has touched every day of the week, namely Sunday, Friday, Wednesday, Monday, Saturday, Thursday, and Tuesday, for indeed it runs through them in this order. So the first thing to see is that we seem to be talking about epacts again, but these are solar epacts rather than lunar epacts, and solar epacts is another term for concurrents. But it's probably easier to remember these as just concurrents and lunar epacts as just epacts. That's what Dionysius did in those first calculations we saw. Anyway, whether you call them concurrents or solar epacts, the important thing is that they're the number of days by which the year exceeds a full number of weeks. Every solar year is 1 day longer than 52 weeks, except leap years, and they're 2 days longer than 52 weeks. For the purposes of our calculations, we have to treat these as cumulative. As Bede says, these run in a 28-year cycle, so they can't be easily memorized for each year of the 19-year cycle. Not every year 1 has the same number of concurrents, and so on. To have a recurring cycle of matched up epacts and concurrents, you'd have to make it 19 times 28 years, i.e. 532 years, and reasonably most people don't have memories that good. So instead of worrying about memorizing them, let's work out how to calculate them. And we're back to Dionysius here. If you wish to know the solar editions, that is, the concurrent days of the week, take the number of years which there have been from the incarnation of the Lord, say 525, and always add a quarter of this number of the years there have been to this number, that is 131, which now makes 656. Add 4 to this, which makes 660. Divide this by 7, which leaves a remainder of 2. There are 2 solar epacts. Okay, let's boil it down to the essentials. First, divide the number of the year by 4, and although he doesn't say this explicitly, we're evidently meant to round down to an integer. If the answer is an integer already, it's because the year is a leap year. Next, we add this number to the number of the year and add a number 4. Then, we divide the result of this addition by 7, and the remainder is the number of concurrents. If there isn't a remainder, the extra days have now added up to a full week. It actually doesn't matter whether we give the value 0 or 7 in this case. If you can remember all the way back to the very first calculations we saw, we used concurrents in a calculation which involved a division by 7, and we were interested in the remainder. Obviously, if you divide 1 by 7, you get 0 remainder 1. If you add 7 to that 1, you get 8, and if you divide that by 7, you get 1 remainder 1. My point is, if you're dividing by 7, you could add any number of 7s, or none, to your original number, and the remainder would be the same. Anyway, we've now got all the tools we need, so let's recap. The first thing to do is work out what year of the 19-year cycle our year is. We add 1 to the number of the year and divide by 19. The remainder is the year of the cycle, and remember that no remainder means it's the 19th year. Next, we look at the list to see whether the 14th Paschal moon falls in March or April this year. If we're in the year 2, 5, 7, 10, 13, 16, or 18, it's March. And if we're in the year 1, 3, 4, 6, 8, 9, 11, 12, 14, 15, 17, or 19, it's in April. The third thing to do is calculate the number of epacts. We divide the year number by 19, we multiply the remainder by 11, and then we divide the result by 30, and the remainder gives us the number of epacts. Next, we calculate the number of concurrents. We divide the year number by 4 and round the answer down to an integer. We add the result to the number of the year and also add 4. Then we divide the result by 7, and the remainder gives us the number of concurrents. Armed with all that information, we can finally tackle those convoluted-sounding first calculations we saw. So, step 5 is calculating the date of the 14th Paschal moon. If it's in March, subtract the epacts from 36, and the result is the date of the 14th Paschal moon. If it's in April, subtract the epacts from 35 to give the date. If more than 30 remains after the subtraction, that is, if the number of epacts is 0 or very low, subtract an additional 30. I didn't mention this earlier, but this is why at the very start we looked at years 2 and 3 rather than 1, because Dionysius spends quite a long time in his sample calculation for a year 1 talking about this. But we did see earlier why this happens. The epacts have added up to a full extra month, and the extra 30-day month added to the lunar calendar to make up for this means that there are 30 extra days in our calculation which need to be removed. Anyway, now we've done all that, we're ready for the final step, calculating the date of Easter Sunday. If we're in March for the 14th Paschal moon, we add the concurrents to the date which we found in step 5 and also add 4. We divide the result by 7 and the remainder gives the day of the week of the 14th Paschal moon. Remember that 1 is Sunday and no remainder means Saturday. This is the division by 7, which means that it doesn't matter whether you treat 7 concurrents as 7 or 0. If we're in April, add the concurrents to the date of the 14th Paschal moon and also add 7 this time. Then divide by 7, and the remainder gives the day of the week of the 14th Paschal moon. Now, you may be thinking, What's the point of adding this 7 if we're just going to divide by 7 anyway? Well, there isn't a point. I assume Dionysius just wanted to create some sort of symmetry between his two calculations, and so he makes us add a pointless 7 to match up to the 4 we added in March. But anyway, the final thing is that Easter Sunday is the Sunday after the 14th Paschal moon. There we have it then. We know how to calculate the date of Easter, so let's put it into practice. We'll use 664 as an example year so we can see when Easter should have been celebrated in the year of the Synod of Whitby. I should stress that Wilfrid and his party may not have had copies of Dionysius' work to use in their calculations. There were plenty of computists, but the basic method they used will have been along these lines. Their Celtic opponents, as we heard in part 1, focused on the 13th rather than the 14th moon, and apparently either didn't use a 19-year cycle at all, or used a different one. In the back of the book by C.W. Jones, which I've mentioned in the video description, he transcribes the preface and chapter headings of an Irish Computus, but other than that, precise information about Celtic computistical methods is a bit thin on the ground, unfortunately. But, using something like the winning method at Whitby, our first step is to work out what year of the cycle 664 is. So we add 1. 664 plus 1 is 665. Then we divide by 19. 665 divided by 19 is 35 exactly, so no remainder, and that means it's the 19th year of the cycle. So step 2. Is the 14th moon in March or April? Well, looking at the list, we can see that the 19th year means April. Step 3. The epacts. You might remember me saying earlier that the 19th year has 18 epacts, and that is the answer. I suppose medieval computists would have remembered the whole cycle, but in case you didn't remember, let's do the calculation. 664 divided by 19 is 34, remainder 18. 18 times 11 is 198. 198 divided by 30 is 6, remainder 18. So there are 18 epacts. Step 4 then, concurrents. 664 divided by 4 is 166, and it's already an integer, so we don't need to round down. 664 was a leap year. Add 166 to 664, and this makes 830. Add another 4, and this makes 834. Divide by 7, which gives us 119, remainder 1, so there's one concurrent. On to step 5 then, the date of the 14th Paschal moon. We're in April, so we subtract the 18 epacts from 35, which gives 17. So the 14th Paschal moon fell on the 17th of April that year. Finally, step 6, the date of Easter Sunday. We add one concurrent to the date, 17, which makes 18. We're in April, so we add this 18 to 7, which makes 25. We divide 25 by 7, which leaves 3, remainder 4, and Wednesday is the 4th day. So we're on Wednesday the 17th of April, and the next Sunday is 4 days later, which makes it the 21st. So all that means that Easter Sunday in 664 AD was on the 21st of April. Now, I'll put the calculations for the year 1066 in the video description, so you can have a go yourself if you'd like, and then check your calculations against mine. As I said earlier, this method won't get you a correct Easter date in the 21st century for most Christian denominations because of the move to the Gregorian calendar, but with a little tweak you can still impress all your Eastern Orthodox friends with your Easter calculating prowess. If we take 2022, we find that it's the 9th year of the cycle, it has 28 epacts and 4 concurrents. This gives a date for the 14th Paschal moon of Wednesday the 7th of April, which makes Easter Sunday the 11th of April. Now, if you look up the date of Orthodox Easter in 2022, the internet will tell you that it's the 24th of April. So what's gone wrong? Well, the internet is converting the date in the Julian calendar to its Gregorian equivalent. If you look at a calendar, you'll see the 11th of April isn't even a Sunday. Even though Orthodox churches use the Julian calendar, the secular administrations of countries tend to use the Gregorian calendar, so we have to be able to convert our Julian date to a Gregorian one. The Julian calendar is 13 days behind the Gregorian one, so add 13 to the 11th of April, and you get 24. And the point is that what your calendar has as Sunday the 24th of April, 2022, is Sunday the 11th of April, 2022 in the Julian calendar. But if this video has lasted much longer than I hoped, and you're watching this after the year 2100, you'll have to add 14 days, because by then the Julian calendar will be 14 days behind. Churches which use the Gregorian calendar have a different method entirely for calculating Easter, so there isn't an easy tweak you can do to our calculations to work out Catholic or Protestant Easter, I'm afraid. Right then, on that disheartening note, we've completed our mammoth trek through the Synod of Whitby and the Computus. Hope you enjoyed it. Well done if you've come this far, and come back soon for another foray into the past.